Okay, this is David Zierler, Director of the Caltech Heritage Project. It's Friday, May 27th, 2022. I'm delighted to be here with Professor David Jackson. Dave, it's great to be with you. Thank you for joining me today.
Well, it's so good to be here. I enjoy this discussion.
Dave, to start, would you please tell me your title and institutional affiliation?
Okay, right now I'm a retired, let's call it emeritus professor of geophysics at UCLA. And I retired in about 10 years ago. So I've got a long history at UCLA and, of course, at Caltech, MIT as well.
Dave, are you enjoying a full retirement? Are you active at all? Are you staying on top of the literature?
Uh, you know what retirement means. It means you change the direction of flow of money from a salary to some other kind of support. No, I'm actively involved in research as well, and paying attention to students who are at UCLA, trying to understand what they're doing and interact with them as well.
Given that you're still active, what are you currently working on?
Well, I'm currently working on understanding some geological data that have been compiled by other people and are related to understanding the future of earthquakes that may happen. And I'm doing statistical analysis on those data. And I'm also working on a global model of earthquake occurrence of magnitude 7 and larger earthquakes. And so that's also more a statistical thing than straight seismological.
Dave, thinking about future earthquakes, does that mean that this work might get us somewhat closer to earthquake prediction?
That's what I think a lot of people, almost all seismologists, hope for. I'm someone who doubts that predicting the times of earthquakes is going to be very successful. I think the places of earthquakes and the kind of earthquakes that may happen and what's going to happen in the event of an earthquake already occurring, those things I think we can deal with. But trying to predict the times is, I think, a long way in the future and maybe never going to happen.
Now, if it never happens, to what extent is that a statement about our limitations with sensing and technology? And to what extent is it simply a fact that perhaps the Earth itself doesn't know when an earthquake is going to happen?
A lot of both, but the fact that earthquakes occur below the surface of the Earth, maybe 5 miles or deeper, and then many global earthquakes a lot deeper, those we just can't observe directly. And the other thing is that you need a long time record. And we didn't observe many earthquakes, before, say, 1900 in any kind of detail. And we can't turn back the clock and understand earthquakes that, have happened a long time before. So that's one of the reasons I'm pretty pessimistic about this. And I might mention that at the Seismo lab, there have been lots of discussions about the predictability of earthquakes. And there are some optimists and some pessimists. I shouldn't call myself a pessimist, but let's just say I'm much more inclined to think the problem is maybe unfathomably complicated.
Dave, over the course of your career, have you been more on the theoretical side or more on the observational experimentation side?
A mix of both, more on the observational and more trying to understand, the implications of earthquakes that have happened without having to do a lot of mathematical things. But my statistical research is definitely on the mathematical side.
How big a role has modeling played in your career, specifically once computers started to get really powerful?
It's again a kind of an intermediate story. There are people who do much more detailed modeling than what I do. But I do modeling and I use existing models putting in data from recent earthquakes, or in some cases past earthquakes, and trying to understand how those data fit into the models. But I'm not creating anything that's a radically new model.
Dave, a few administrative questions. Have you
Okay.
been part of the Southern California Earthquake Center, or SCEC, from its inception?
Yes. Um, I was one of the people who helped to write the original proposal that went to the National Science
Oh,
Foundation
wow.
for SCEC.
Who
So
were the others?
Tom Henye from USC was sort of partnered with me in writing the document, and we were all sort of taking guidance from Kay Aki, who was a professor at that time at USC, and he was the one who really got the ball rolling on the Southern California Earthquake Center.
What was the need for it? What did you express in the proposal?
The need for was a way of integrating what we knew about earthquakes with what could be done to kind of deal with the risks that are posed by earthquakes. And there were a lot of approaches to that, a lot of measurements of earthquake data, seismological data, and geological data, and a lot of modeling going on with that. But it was mostly done by individuals all competing with one another, which is a very healthy process. But Aki recommended and noticed that, so I should say, realized that if people could work together, some of the observational data could be collected in a more organized way, and that people could get together in a kind of a periodic process and discuss their results, still competing, but also, listening and talking. And it was, I think, a very good and important perception. And by bringing together scientists, we started with a group of about six universities, and now it's grown to 50 some different universities. And Aki's no longer with us. He, retired from SCEC, the Southern California Earthquake Center, I think in 1997 or something like that, quite some time ago. And now he's deceased.
What were the initial institutions involved in the creation of SCEC? Was it UCLA and USC initially?
I was UCLA, USC, the United States Geological Survey was part of it, and Scripps Institution in San Diego was also part of it.
But Caltech and Seismo Lab were not.
They were a little reluctant to get involved,
Huh.
and I think that's an interesting story about seismological history
Yeah.
in California. The U.S. Geological Survey was a major institution, and they were kind of dealing with mostly Central and Northern California. Caltech was definitely the place in Southern California. And so there was some competition going on. Part of Aki's idea was to sort of bridge these gaps, the divides that occurred. But Caltech kind of thought, hey, these people are maybe invading our territory, and we've got a lot to do already. And so I think they were a little bit reluctant at the moment, but now they're very, very strongly participating, and there's no question that it's pretty much a unified group of researchers.
Dave, Caltech, sorry, my dog is excited in the background.
Okay.
Caltech's reluctance to join SCEC initially, does that play at all into the story about Caltech being slow to the plate tectonic revolution also? Are those interconnected stories in your view?
I think not. I think the plate tectonic story was a global story and involved a lot of geologists and seismologists, well beyond Caltech and MIT and the Scripps Institution, and other universities throughout the world. And it took a long time for that to develop. But I wouldn't say that Caltech was behind in that. I think we were all behind.
When finally did the Caltech and Seismo Lab get involved in SCAC?
Well, it was partially involved at the very beginning, and it grew. But I think it was largely because Caltech had so much going on, and they sort of regarded SCAC as being a way for the other universities to catch up. And I couldn't put a date on it, but SCIC started in about 1990, a little bit before that in terms of that proposal that was written and so forth. Um, so there wasn't really a date when Caltech said, "Oh, we better get involved," because there were several people from Caltech who were involved in SCIC from the beginning.
Dave, have most of your collaborations regionally been through SCEC, or have you pursued independent collaborations at other institutions, including the USGS?
I have definitely been involved strongly in SCIC, but with other universities as well, and some global partners. And because SCIC is focused on Southern California, and earthquakes are not focused in that way, although clearly earthquakes provide a focus in Southern California. But many of us were also involved in global studies, and some studies, my statistical studies, aren't necessarily focused on SCIC.
Dave, a few questions administratively about geophysics and seismology at UCLA. So at UCLA, is there an analog to the Seismo Lab? Is there a program that's sort of separate from the rest of the institution?
There was a strong geophysical group at UCLA before SCIC started, and the primary leader of that was Leon Napoff, and he had been at Caltech, PhD from Caltech, so he was very strongly connected with Frank Press and with the other leaders of the Seismo Lab, and also he was very strongly connected with Kay Aki. And when SCIC started, Kay Aki invited Leon and some people from the Lamont Geophysical Institute in New York, and the U.S. Geological Survey, I think I mentioned, and Aki and myself. So there was a kind of a small group of people who said, "Yeah, we really ought to do this," and Caltech didn't want to participate really at that time, sort of formulating the ideas.
Dave, in your career, how active have you been in the AGU?
Oh, I think I got a pin of some kind a few years ago as a 50-year veteran of the AGU. I went to my first AGU probably 1966 or 1967, and have been, attending AGU meetings pretty much all the time. There were one or two that I missed.
And is that for geophysics and seismology for you? Is that the most important scientific society?
Oh, it certainly was. Now the Seismological Society in California is very much a strong participant, and there are global organizations like the International Union of Geology and Geophysics, which also are very strongly involved. So again, I wouldn't say that there's a single most dominant society, but certainly the AGU is very strongly uh, in a position of leadership.
Dave, just a headline news question. Only a few days ago, there was an earthquake, something like 4.3 in the Los Angeles area. Are you set up where you're ready to look at earthquakes as they happen?
Um, let's say I'm set up such that I could. I generally focus on earthquakes bigger than magnitude 6 in California. So I don't pay a lot of attention to magnitude 4 and 5 earthquakes. I notice them, but sometimes I found out about them because a reporter calls me up and says, "What was that about?" And first thing I do is I say, "Well, tell me what you know about
Yeah.
it."
Dave, I've learned that there's a few schools of thought here in California, of course. One is that we're waiting for the big one, however long that might take and however big it might be. And the
Yes.
other is there's really nothing to wait for because there's not necessarily a cycle to these things. Where do you fall in on those debates?
No cycle. And I resist the temptation to talk about the big one because I think the article is wrong. A big earthquake may happen at any time. And we know that several have happened, but I wouldn't describe it as being a singular thing to look for. So I don't like talking about the big one.
How
Some
big
big ones are going to happen.
how big theoretically could an earthquake get in California?
I would say again, I resist trying to talk about details in a situation like that. We don't know. The biggest one that we know about having happened already are about magnitude 8 and the 1906 earthquake in, sometimes called the San Francisco earthquake. And there was an 1857 earthquake in Southern California. Um, we didn't have good seismological measurements at that time, so we don't really know how big those were. And a lot of people expect that those are, the primary types of earthquakes that may happen even in the same place. Um, I think we don't know that. We can have big earthquakes in lots of other places. And the
Which
biggest recorded earthquake in Southern California was in 1952, and that was not on the San Andreas, and it's not been followed by any earthquakes, very much like that. But that was bigger than magnitude 7.5. So uh, I think surprises are coming. And that's my prediction about it.
whether it's a big one or the big one in Southern California, how well prepared do you think we are right now between advances in earthquake engineering and also advances in earthquake early warning?
Um, Another difficult question. It sort of requires first for us to talk about acceptable risk. And we know some of the risks that happen with earthquakes. We have a pretty good idea of how frequently damaging earthquakes may occur at a certain level of damage. And we know the places where earthquakes could be most damaging if an earthquake were to happen. And Los Angeles is definitely one of those places, and I include Pasadena in that description. But there are a lot of other problems that people address, and those are also underserved in terms of our facility for dealing with them. And for example, COVID is something. Should we be diverting more attention to COVID than to earthquakes? I'd have to say yes. COVID is killing lots and lots of people. The number of people killed by earthquakes in California are a few hundred. And, those are daily death rates. So I would say we are appropriately prepared for earthquakes throughout California. We know what's happening. We've done engineering studies that help us understand how best we can make new buildings safer. Dealing with older buildings is a lot more problematical because, first of all, you can't just make them new, and there are other issues, including people who already live there, and do you move them out and do some serious retrofitting, and it takes years for them to come back. So I would say dealing with all the issues that we have, we shouldn't be embarrassed with the level of preparation that we have. Could we think of all kinds of ways to improve our safety? Yes, but we have to balance that with other needs.
Where do you put the level of sensors that we currently have in Southern California? Are you satisfied that we have enough for all that we need them for?
Um, Again, what's a need? We have very good seismic arrays. Other countries, particularly Japan, have much more coverage with seismic instrumentation, and they have led us in California in sort of showing how to use networks and high density, meaning close together stations, so that we can compare the results of an earthquake at one place with that of another place nearby. That's important in sort of understanding and testing whether or not our understanding of earthquakes is telling us what's happening. Um, so I would say it would be scientifically productive to increase our coverage and put in new kinds of instruments. And we're making some progress, but there's plenty to do there. And I would say that would be very fruitful to increase our expenditures and put in more instrumentation.
Dave, we find ourselves in the midst of a quantum science revolution, and there's a lot of excitement about what quantum sensors can do. Even though
Yeah,
earthquakes are a classical system, do you see a future role for quantum sensors in earthquake prediction and early warning?
I don't really understand what can be done with quantum science and quantum computing. I've read some descriptions of how grand it will be, uh, but I'm not prepared to sort of say um, what's the likely use of the quantum computing in seismology. I go back to my story that there will be surprises.
Well, let's
Um,
go all the way back now to your time at Caltech. First, just to set the stage, as a teenager in high school, were you interested in geology and geophysics and things like that?
I was a curious kid, and I was definitely interested in those things. And I went to a summer program at the Colorado School of Mines when I was at the summer after my junior year in high school, the 11th grade, and I was very much excited by that. Um, and I got started in geophysics from a high school advisor, and she just advised me to apply for every scholarship that did not have my name on it as an exclusion. She said, if see an announcement for a scholarship in biology and you would have fun in biology, apply for it. So I applied for more scholarships. I don't think I set a world record, but I set a lot. Um, and when I got a scholarship in geophysics, I had to go to the dictionary and look it up and find out what it was. But I got the scholarship and I loved it. And the more I found out about geophysics, the more I liked it. And when I got to Caltech, they didn't have exactly the right geophysics program to match my scholarship. It was more about oil exploration at that time. Um, so I went to the Seismo lab and talked with Frank Press, who was the leader at that time, and told him my situation. And he said, "You probably should apply, or that you should go into the physics department at Caltech." He said, "This is the path that most most seismologists take." And he said, your scholarship group, they'll be happy to have you do that. And that was true. I talked to them and they said, "Oh, it would be delighted to have you be in the physics department as long as you go talk to Frank Press and other geophysicists occasionally." And that was great advice.
Dave, was it easy to get an appointment with Frank Press? Was he imposing? Did you feel a little nervous going to talk to him?
Um, he was not imposing. He was very, very friendly. And I'm always, a little reluctant when I knock on somebody's door and not knowing, what kind of reception I would get. But I was not shy in that way. And Frank was really very receptive. He was delighted to have me there. I don't think he had known that, I had applied to be there, or whatever. But when I told him my story, he said, "Well, definitely we'll find a place for you at the Seismo lab and get you a summer job and things like that." And so no reluctance whatsoever on his part or on mine.
Just so I could visualize the process. So this was happening on campus, and they sent you up to the Seismo lab to meet Frank Press.
I don't remember whether my first meeting was up there on San Rafael Avenue or whether it was on campus, because he had an office on campus as well. So I don't remember where that meeting was, but in any case, I was at San Rafael within a week, and meeting with other people there.
What was it like at the old Seismo lab?
Well, it was exciting. People were always ready to go measure something if an earthquake happened. And people were working on building new instruments and finding places to install them. And in those days, they didn't have the sort of telecommunications that we have now. And so we had to find places. I say we because I became involved in these activities as an undergraduate. Find places where we could install seismograph stations on good solid ground, which is better for recording earthquake shaking, and close enough and accessible enough that we could come collect our data on a regular basis and collect it on an irregular basis if an earthquake happened.
Dave,
So I'd say exciting.
what were the
dynamic.
big debates happening at the Seismo lab in the early and mid 1960s?
Well, there were lots of debates. Maybe I could start with a little bit of, my view of the scientific method and how I've seen it, play out at Caltech and MIT and so forth. And I'm sure you probably know that, kind of the mantra about you make observations and you get curious, and so you ask some questions, and then you develop a theory, and then you come back and make some new observations, we call them predictions, to sort of validate or invalidate your theory. And the first step to make these observations sometimes is made just by guesswork. Notice that some buildings collapse or that they're shaking in the ground, and there may be some seismic stations around, and you observe those. And so then you make some guesses about what caused the shaking or what you observed. And those two steps can be quite different. The observation can be you just walking around and looking at things, or looking at some data that somebody has shown you. And then when you try and make the explanation, it involves some more theory, sometimes some mathematics, sometimes some kind of new observations. And then you get back to something that is a little bit uh, less fixed. You're trying to envision a theory, and then you come back and you test that with some new observations, which again put you on the ground, and you take some seismometers with you and put them in the right place at the right time. So those four steps, I used to think when I was in high school that one person did all that. You see some geraniums and plant some seeds and you water them and see what happens and how much watering you do. But in real life, most of the scientific steps take a long time. And just to categorize the observations that get you started in the scientific method involves a lot of work. And that's what was happening at the Seismo lab at San Rafael. A lot of it was just, putting out seismographs in places where if they were shaking, we could measure it and get the data back. And then there's a theoretical step of kind of coming up with some explanations. And so when you talk about possible debates, it's not just a matter of debates, it's a matter of different styles of research when people see what's important. And there are people who are, terribly important in building instruments and making the seismographs and making sure that when the ground shakes, that you get some data that tells you, what that shaking really was, rather than just some sort of, random yes or no or something like that. And then when you get into the third step, the step of making a kind of a prediction of what might happen, that can involve a lot of analysis, but it can also involve a lot of just interpretation of what you've already seen. And then there's the testing step, which is how do you make an experiment that will look at things that haven't happened yet or that you haven't measured yet and compare that with your theories. And a lot of the prizes come at the AGU from that third step where you're taking a hypothesis and saying, here's what I think happened, and describing it in a way that it could be testable. And then at the very end, there's the step that may involve some statistics, and that's where I think I fit in, mostly to this process. But what happened at Caltech was a natural evolution of the importance of those steps, because there hadn't been a lot of carefully observed earthquakes in California in 1961 when I, came into Caltech. And what seismologists talked about were the global earthquakes, the big ones, the 1960, 1964 earthquakes, and the earthquake in, the 1906 earthquake in San Francisco. People talked a lot about that, but there wasn't a lot of data on that. And so we were in the situation of kind of collecting data and trying to make a story out of what we could see. But in the 60s, computers became usable. We had more data produced by Gutenberg and Richter and people like that in California and in the Berkeley lab in Northern California. So the shift to a more analytical type of operation was taking place. And Frank Press coming into the Seismo lab was very much a part of that. He was an analyst, and he had written a book with some colleagues about the theory of earthquake wave propagation. And this is something that hadn't been that important in the early days because we didn't have the kind of data that would, be testable by these kind of theories. But when Frank Press came in, this was a paradigm shift. maybe paradigm is not quite the right word because it wasn't um, a change in the ideas of what may be going on. It's a change in the importance of getting observational data and then putting it into a kind of an analytical theory. Um, I came in, I didn't know where I would fit it in, this sort of balance. And it's only after kind of seeing different universities in this kind of change in what's important that I could get a better picture of the scientific method. I thought I was going to come in and make some observations and plant some germaniums on a fault and see what happened. Didn't work that way.
Dave, a more prosaic question. Could you take courses at the Seismo lab, or that was strictly laboratory and observational work?
That's a good question because the answer depends on the difference between undergraduate students, graduate students, postdoctoral people, professors, and all those are, of course, involved in the research. I took classes full time. I was a full time Caltech student, and I was taking 5 classes at one time. For one semester, one quarter. We didn't have semesters, and so for me, I had to live on campus, and I had to thumb a ride up to San Rafael to visit people at the Seismo lab.
So there was no shuttle. You had to get up there on your own.
I did, yeah. Eventually, I got a car, but and there were graduate students who maybe were taking 1 or 2 advanced classes, and they could reside at the Seismo lab up on San Rafael, or at least spend a lot more time there than I did. And then, of course, the postdoctoral people, some of them spent most of their time on campus, and some of them were spending their time, up at the lab. And so most of my time was spent on campus. And I would see Frank Press when I could, sometimes on campus. And I loved going to the lab. So I did that as much as I could.
Dave, you already suggested as much, but as an undergraduate, if you showed the inclination and the initiative, could you be involved in research?
Yes. Yes.
So what kinds of things did you do as an undergraduate?
Well, one of the things I did was look at data provided by other institutions. And I actually was a co-author on a paper with Frank Press in, I think it was 1965 or 66, on the Alaskan earthquake in 1964. And so data came in from U.S. Geological Survey and others. And we had an analyst named somebody, I forget her last name, who was also, harvesting a lot of data. And so I was sitting at my desk and using a very elementary computer at the time to do some calculations of looking at the aftershocks of that earthquake. And I was also involved in some field studies when someone was going to a new place to install a seismometer or something like that. I would tag along, and occasionally I was asked to go to one of those locations and just look to see if the instrument was in place and if there'd been any new construction or anything like that at the site that would affect the observations. So there were a lot of things that were easy for me to just take as a suggestion as something I might do. And then there was this project with the aftershocks of the Alaskan earthquake that I had the data and I needed to sit down and do the computing. And I knew what to do, but I had to find the time to do it.
Did you interact at all with graduate students and postdocs on this research, or they were more geared toward things that an undergraduate could do?
I would say in my case, it was more for undergraduate things just because my time was programmed by the the, the institute itself and courses that I had to take. I did know, a number of the grad students and would chat with them, and we would have weekly get-togethers and just talk about, what was new, and those were on campus, and so it was pretty easy to interact with that. But I would say the atmosphere was such that anybody who showed an interest would be invited to be involved in it. And these sort of weekly get-togethers were important in that role. The grad student grad students would have their own ideas, and so we definitely were brought into some investigations by the grad students as well as by the faculty.
Dave, at the Seismo lab, were computers, or at least the very earliest versions of computers, already in use when you were an undergrad?
You bet. And in fact, the computers were pretty elementary. They were giant, they were refrigerator-sized computers, and they couldn't do what you could do on your cell phone. And one of my jobs was to do some editing of paper tapes. So we didn't even have IBM cards in use at that time. We had these paper tapes that had a bunch of little punch holes in the tapes. And sometimes the tapes would break, or somebody would, in their programming, instruct the computer to punch a hole in the wrong place. And so you had to go take the tape, cut out the offending piece. It's almost like a kind of surgery, and then put in some blank tape that could now be repunched, and put that into a machine that would read those instructions again. And at the end, you'd get this long paper tape with a lot of holes in it. And so part of my job was to look at those holes, translate them into the computer instructions, and see if the instructions were right, and then have to correct them, which is most of the time.
Dave, besides Frank Press, who are some of the other faculty who were influential for you as an undergrad?
Well, Don Anderson was definitely influential, and he was at the Seismo lab, but again, he had an office at Caltech. And I had a start on a job with David Harkrider. Frank Press put me together with David at one time because David was getting a project started, and Frank just thought, no, there's an idea. So I did work with David Harkrider for a while, but it didn't take too long before I got to punching the paper tapes and going out the field and trying to, examine some of the seismic installations.
What areas were people like Press and Harkrider and Anderson collaborating on, and where were they off pursuing their own independent research?
That I don't have a very good picture of. I mean, I knew that on these weekly meetings, people would get together and chat, and it all seemed to be very much collaborative chat. But Don Anderson was more interested in the properties of the materials through which seismic waves passed. So he was part of this progression from open observations to theory to sort of testing the theory and building some tests. So he was in kind of another wing of that. Frank Press was definitely in the analytical wing, where you've got some observations and you're trying to explain them mathematically. But Frank also was very good at instrumental design. So he developed some new seismographs that then became standards throughout the US and in Japan and some other places. And to my knowledge, for example, Don Anderson didn't do that part of the job, but I don't know. I think there was a lot of collaboration, but definitely in different directions.
Dave, what about the founding generation of the Seismo Lab? Did you ever get to meet any of those people? Would they come around?
I met Richter. I think I met Benioff early in the day, but I don't remember very much, what we discussed. Um, um, but I do know that there was some resistance when Frank Press was appointed there because of this evolution of the importance from straight observational data to the analytical part. And so some people thought maybe that Benioff or Richter should have been appointed uh, because they had already a history at Caltech, and Frank Press was coming in from the outside. And I'm not sure who made those kind of decisions, but obviously they recognized that having computational capabilities and the analytical capabilities that Press had, that he would be an addition to the armory at Caltech. Uh, so I was 18 at the time, so
Right.
I really get to know all these people. And remember, I was still looking up in the dictionary what geophysics was.
Right. Dave, did you spend any time at JPL? And more generally, were there any institutional collaborations between the Seismo Lab and JPL?
There were, didn't recognize them as important parts of the development of the Seismo Lab, but I did meet people from JPL, and I lived very near to the Arroyo Seco, so I would go hiking uh, at, uh, at JPL. And I know that as time went on, JPL at Caltech got much more involved in seismology. But that was more after I left Caltech and went to MIT.
Dave, what about beyond Caltech? Do you have a memory of the Seismo Lab being an intellectual magnet, a place where people in the field would come and visit, share papers, learn what was going on, that kind of thing?
Oh, you bet, you bet. And When I was at MIT, I mean, I followed Frank Press to MIT. He went to be the chair of the department at MIT, and he suggested definitely I should apply, which I would have anyway. But he made a very strong case, and I'm sure it made it easier for me to get into MIT because Frank had recommended me. But my family home was in Altadena, and so I would come to my family home for summertime and come to the Seismo lab and discuss with people. And when I went to the American Geophysical Union meetings, I would, meet my buddies from Caltech and go to hear their presentations and read the papers that they were writing. And there's no question that the Seismo Lab was a huge, strong magnet bringing people in. And at MIT, many of the people that I met had been at Caltech and come to MIT as professors. Nafi Taxos was one of those, and Sean Beeler. I don't know if you've encountered him,
Mm-hmm.
but then he came to MIT, and so there was a very strong connection between MIT and Caltech, and also Scripps, and also the Lamont Geological Observatory. Those people, we were all keeping track of each other's progress and paying attention.
Dave, what about the culture of data sharing? In other words, before the internet and networking that allowed data to flow freely, from lab to lab, from scholar to scholar, was your sense that the Seismo Lab had data that was in some sense proprietary, that you had to come to the Seismo Lab in order to access it?
I think the answer is yes, but it wasn't necessarily that people resisted sharing it. There was some resistance, of course, because people had worked hard to put those seismometers in the ground and record the data over a period of years. and they had a plan for testing a hypothesis, and so that was going to be uh, their mark of success, and they could test that. So it was a little bit a kind of a personal trove of information. And that's part of what SCEC was all about.
Mm-hmm.
SCEC recognized that to make scientific progress, data sharing would be important. And yet you still need to respect the privacy and the the work that's done by somebody collecting those data. So the idea behind SCEC was to share these data and share the credit and make it clear, who's done the primary work in developing observations and tests. So
Dave,
it was progress.
was there a senior thesis or a capstone project for you at the Seismo Lab?
It was really this story about the Alaskan earthquake, and my part in this publication. But otherwise, I did not have what you would call a capstone project.
Now, as you indicated, you went with Frank Press off to MIT. Was the timing perfect? Was he going just at the time when you were graduating?
He really left before I was graduating, but yeah, the timing was perfect. I mean, had I been 2 years later or 2 years earlier, might have been a different story.
Not that he would have confided in a 20-year-old, but do you have any sense of his motivations, what was attractive to him about going to MIT?
Well, I knew that he also felt that the tide was turning toward analytical work.
Mm-hmm.
And he was very good in mathematics. And I think MIT was attracted to him in the same way that Caltech was. MIT was more geological, as Caltech had been. The geology was a much more important part of earthquake studies. And so I think MIT felt they needed him, or they needed somebody like him. And what discussions they had in their boardrooms, I don't know, and what role money had, I don't know either. I don't think that's a very important reason for changing fields for somebody like Caltech, or somebody like Frank Press, who would be rewarded in any case. I mean, he was hugely successful. But I think he saw scientific advantages in using what MIT had available, and they definitely felt they had advantages in using his talents.
And what was available at MIT? Where were they ahead of the curve relative to Caltech at that point?
Good question. I think in some regional geology, Caltech geology was really focused on California. And at MIT, they were more involved in global geology, and at least continental geology. And they had oceanography as part of their program. They had the Woods Hole Oceanographic Institute that was pretty closely related to their department. And so when plate tectonics began to be debated, that was a good place to be, because oceanographic data were coming in, the kind of shipboard magnetometer data that were a big role in sort of convincing people about plate tectonics. So MIT had these kind of data, these kind of facilities that Caltech didn't have.
Did you apply elsewhere for graduate school, or with Frank Press that was a simple decision just to go there?
Well, I told you about my high school advisor.
Yeah.
I remembered her advice. So I applied to quite a few places. I think I applied to 6 or 8 places. And that included MIT, included Harvard, including Caltech again. And I don't think UCLA at that time, but I did apply to a number of different places. But I was hoping for MIT, and so it was an easy choice.
And would Press be your thesis advisor at MIT?
Um, he was kind of a co-advisor. He was getting his feet on the ground at MIT, and so he was not quite so much involved in advising individual students, but he was always open. I mean, his office was always open, and I talked with him maybe not every week, but fairly frequently. And my advisor was Gene Simmons, who was more a geologist, but kind of jack of all trades. And he was a very good advisor for me. Um, and a lot of reasons, but for one, uh, he told me that I was going to be responsible for my graduate education and my thesis. And he wanted me to tell him about it, but he wasn't going to tell me what to do. And that was perfect for me.
The hands-off approach worked for
Oh
you.
yeah, yeah, it was great. And then Frank Press was quite like that as well. I mean, he would give me ideas, and when I met him when I was 18, I needed some more direct suggestions. But by the time I went to graduate school, I had a lot of suggestions that I was already working on.
Dave, it's impossible to answer this. It's a counterfactual, but in going to MIT, whereas you emphasized there was a greater emphasis on the analytical approach, do you think that made your thesis more analytical than it otherwise would have been had you stayed at Caltech?
I don't think so. My thesis was some experimental observations and a lot of just putting together things that I had read and make them into a story. So I wasn't doing the kind of analysis that Frank Press was doing at MIT. So I don't think that would have made much difference.
How much field work did you do for your thesis?
Not a lot. At MIT, you don't have the quick trip to the San Andreas Fault, or you don't have many neighborhood earthquakes to deal with. So my work was more indoors, but we did have yearly field trips and things like that that were not particularly aimed at my kind of thesis work. In fact, I was doing an experiment on some rocks and ceramics to try to measure what caused energy to be absorbed within the material and taken out of the seismic waves that might go through them. And so that was quite different from what I had been doing at Caltech, but it followed on one of the major questions that people were discussing at Caltech, which is what causes the attenuation of seismic waves.
Mm-hmm.
When you try to understand, the amplitude of the waves and why the shaking is stronger in some places than in others, and why it gets weaker as you go further away from an earthquake, and how much that depends on the size of the earthquake and those kinds of things. So I follow that into a physical experiment, and I then went back to Caltech on my summer vacations, and also, talking with Don Anderson, who was involved in some work that I did. And so it was definitely a follow-on to my Caltech work, but quite different from what I had done on campus.
Dave, even from earlier in the decade, were there computational advances that you were able to take advantage of for your PhD?
Oh yeah, yeah. Some of them being books that people had written, and some of it being the speed with which you could analyze data And so in my classes and my work analyzing the experiment that I've been doing, um, I was using the computer, quite often. And then when I went to UCLA as a faculty member, same story. The computer usage was growing. And I think once you recognize the need for analysis, you're going to be using the computer a lot.
Dave, what would you say were your principal conclusions or contributions with your thesis research?
Well, it was several papers on the ideas about what had caused the seismic attenuation to be important and the effects of temperature and pressure on those. So I was doing laboratory work, but then able to use my laboratory work as part of the kind of hypothesis that you use in that third step of the scientific method. And then that's been followed by other people also doing more laboratory work. And there's actually a fellow in Australia uh, who's also of the name Jackson, who's doing a similar kind of experiment to what I was doing, but much more elaborate and much more controlled and so forth. But anyway, it's been a long-standing question about what happens within the rocks when a seismic wave passes and deforms the rocks, and then it absorbs some energy in that passage. And so I contributed a pretty detailed hypothesis that could then be tested against laboratory rocks and against the seismic waves themselves. And I regard that as my contribution.
What aspects of the thesis have held up over time, and what has changed as a result of new theory, new observations?
Um, I think the general ideas have held up over time. People have come through and looked at a lot of different kinds of rocks. And one of the questions that arose from my thesis is, what do the little grains in rock do? Because they shift around like that when a seismic wave is coming along. And so there's an interaction between what's in the volume of a grain and what's at the surface of a grain. And one of the things that's held up in my work is that interaction is very important, that you can't isolate one from the other. You get a pure rock with giant grains, and its behavior will be a lot different from the same material, but broken up into little grains and then welded together by temperature and pressure. And so that behavior would be quite different. And that's something that wasn't appreciated much in the seismological context because we didn't have that kind of data. An earthquake would happen, and we'd measure the amplitude of the waves at some distance in lots of different places. And for us, it was all homogeneous material. And so I think I managed to change that story, and that's held up very well.
Dave, unrelated question on the social side. Being in Cambridge, Massachusetts in the late 1960s, were you political at all?
Yes, I was. And I had a couple of conversations with Frank Press. That's one of the ways where he was my kind of associate advisor. And I discussed with him because I knew him better. And I knew the importance of his influence, seismologically. And I knew that also he was politically involved and involved in trying to do something to help out people, to make the work applicable. And I was at the time, possibly threatened with going to Vietnam as part of the Vietnam War. And I was a conscientious objector, and I talked to him about that. And he was very helpful. And he would tell me, I really understand your depth of concern about what's going on in the country and what people need. And he had said, but, play to your strengths. Take the things that you know how to do and figure out ways that you can make them help fulfill some of your interests and your needs in politics and in kind of making the world better. And so we would talk about that on occasion, and it was very helpful to me.
Could you
I didn't
tell?
drop out of school. I think he was afraid I might be ready to do that, and I might have if the Vietnam War had gone in a different direction, or if I'd been, called to serve.
Dave, in the way that you interacted with Frank on these issues, could you tell, did he already seem to be on a trajectory that would put him in Jimmy Carter's White House and leading the National Academy?
I would say it wasn't a surprise at all. He was very much involved in the space program. In fact, one of the instruments that he developed was then, modified and taken to the moon. And so he definitely was much broader than earthquake seismology. And he was, certainly deeply involved in, advancing plate tectonic theory. And now through planetary geophysics and building instruments, he knew a lot about putting pieces together and putting teams together. I would maybe I lost my train of thought, but anyway, he was really good at building teams, and I think had a very broad sense. And so his role in the National Academy of Sciences and as the science advisor, I think was not obvious, but certainly unsurprising for a lot of people.
Dave, after you defended, what opportunities were available to you? Where were you looking to get a job or a postdoc?
I knew that I wanted to be still involved in science, in geophysics. And so, again, I searched broadly and came up with UCLA as a place that was interested in me and where I could do, a lot of productive work. So that's what I chose. I also applied to Stanford, MIT, Caltech again, Scripps Institute. So I had a lot of possibilities, but UCLA worked out best for me. And when I first got there, I followed my thesis work. I was talking about attenuation of seismic waves, more from the seismological perspective rather than the laboratory, instrumental perspective. But then in talking with Leon Napoff, who was also just, a great intellectual leader and advisor for me, got more involved in California earthquakes. And then we had this earthquake in Parkfield in 1966. It was after that I went to UCLA, but that was a subject of big interest in the California seismological community. So I went more into earthquake seismology rather than I had been at MIT.
Now, was it initially a postdoc at UCLA or you joined the faculty straight away?
It was sort of middle ground. I had an in-residence professorship, which was an academic position. It didn't necessarily involve any teaching. It was kind of a one step up from a postdoc. And then it was after, I think, about 2 years that I got put into a regular faculty position.
Now, how new was UCLA to you, being at Caltech, being in, growing up there?
Obviously a different kind of institution, um, but Caltech is very small, MIT much larger, kind of middle ground, and UCLA is a whole city. Um, so it was a different environment. Um, but I didn't find the change to be radical in any sense. And I had um, academic heroes in all those places. And so I didn't find it that much of a change. It didn't take long before I was involved in teaching classes, and that was a change. But I always loved teaching anyway. So again, I really welcomed getting into the classroom.
Now, how soon after you joined the faculty were the origins of SCEC already up and running?
That was quite a while. I mean, I joined the faculty in 1968 or 69, 1969, and SCAC really started in 1989, I would say, these discussions with Kay Aki and Leon Napoff and other people at USGS. Those discussions resulted in this proposal that I was part of writing in about early 1990. And so that was a long time in coming.
Now, being back in Southern California, being closer to the field work, how did that change your research agenda?
Oh, quite a bit. I spent a fair amount of time planning experiments. I wasn't an instrument builder, as Frank Press had been, but I was very much involved in sort of deciding where seismograph instruments ought to go in order to deal with future earthquakes. And part of that is putting together one of these hypotheses about where earthquakes are going to happen, and trying to make a question out of what's going to happen on a particular fault in the future. So that was new to me, that kind of planning and teamwork that involved now my directing a bunch of associates to come out and do some field work. And so it was fun. I enjoyed that, but that was a new step for me.
Dave, some technical questions. What work did you do early in your career on Rayleigh waves?
Not a lot, really. Frank Press and Leon Napoff both were involved in modeling wave propagation. I was involved in taking observed data and looking at the amplitudes of those Rayleigh waves and saying, okay, what kind of rock attenuation is involved in stealing energy out of those waves. But I was not doing any theoretical work and not making new observations of Rayleigh waves.
A new term to me. You wrote about the edge hog method. What is that?
The edge problem is one sort of involved in mathematical modeling. Um, Edges are discontinuities in the physical material. And when a wave hits a discontinuity, it can scatter the energy and act almost as an earthquake itself in sending waves through the medium. And maybe an easy way to visualize that is if the windshield of your car has some little pits in it from sand grades and so forth like that, and the sun is shining on your windshield, you see bright speckles coming in. And those are discontinuities. And the edges are sort of bigger discontinuities, but they have the same effect of diffracting seismic waves. And there are theoretical problems, and Leon Napoff was very much involved in that, trying to solve the mathematical problems of how to understand the diffraction that takes place, and how big a discontinuity do you need, and what's the effect of short wavelength waves and long wavelength waves and things like that.
Dave, what's the application of linear inverse theory to your work?
Oh, it's everything. It's uh, basically the um, technical approach to solving a lot of coupled equations. So when you have an equation um, about, say, seismic attenuation at one high frequency, and then you have also measured attenuation at much longer periods, lower frequencies, and you put those together, and they're coupled in the sense that the waves have traveled through the same medium, maybe hit the same edges, but they have a different effect on what you observe. And so this linear inversion theory is taking a whole set of equations and lining them up in such a way that you can harvest the um, the information you have about the material that the waves have gone through, and harvest all the data that collected in those ways and put those together so that you're digging out the stuff that's in all the different equations. And linear means that these equations are ones in which if you double the size of the input, you also double the output. And it's much more complicated when it's nonlinear. And so you start with the linear theory. I did, and a lot of people uh, sort of stop with that because the linear theory is also very difficult to handle, and a lot of problems. We know they're not really linear problems, but a good approximation is that you double the input, you double the output, and so that's very useful theory. And there are books written about it all the time, and it's useful not just in seismology and geophysics, but biology, economics, the whole world, I think, depends on inverse theory.
Dave, in the context of how you use the term, what does a priori data mean? In other words, isn't all data a priori?
No. Um, we start with some ideas about, these linear inverse problems often don't have enough data to tell you the answer you want, to put together the properties that affect all of these different equations you're linking together. There just may not be enough data to answer those properties. So if you mathematically pose the problem, you say, how much do I know about, say, the um, the density as it increases in the Earth's crust and mantle. We know it changes, but we can measure things that affect the density variation, but we can't find an answer, yes or no, that there's a limit anywhere in there. And so a lot of problems result mathematically in something that there's no answer. You did your measurements, you did your inverse theory correctly, and the answer is completely ambiguous. Then it helps a lot to say, well, the density variation in the Earth is within limits. It comes from rocks. We have some rocks in the laboratory. We know that rock density is around 2.5 for a lot of crustal rocks, and gets to be maybe 5, inside the iron part of the mantle. So you got a range, and so the a priori is that range
I see.
you put into it, and then you get new data. You measure gravity. You didn't have that before, so that's not part of your a priori, but that's new. And then you put those things together, and there are some mathematical techniques for putting together sensible a priori data and getting believable results that you can hang your hat on with some new information.
Dave, was there a period in your career when you were most intensively focused on crustal deformation?
Yes. Um, when I got started in the earthquake work at UCLA, um, then one of the basic problems is how could we understand the stress that's accumulating from past earthquakes and possibly building up for future earthquakes. Certainly building up, but where and when and to what extent, and what's the effect of that stress on future earthquakes uh, in opposition to lifting up the crust. And some of the energy goes into things that you can measure not with seismic waves, but with geodesy, measuring leveling changes and taking a laser and running it between two mountaintops and finding out that the distance between the two mountaintops has changed. And a lot of it is because of faults, and the faults move, and the mountaintops move with the different sides of the fault. And so that was one of the tools that became very important in sort of understanding the past and the future of earthquakes. So I got involved in trying to deal with some very simple mathematical models for explaining what happens when a fault is deformed or when an earthquake happens, and trying to use that to look at the future.
Dave, tell me about the development of the magnetometer array in Southern California and what that meant for your research.
Um, that was a proposed hypothesis that may have had some relation to future earthquakes. And the idea was that this stress that's building up, that we're talking about measuring with geodetic work, also has a piezomagnetic effect. And it's what happens in a phonograph needle when you put a record on and that little needle moves back and forth. It causes a stress in the phonograph needle, and you can record that. So that's where a lot of our music comes from. Nowadays, no phonograph needles, but in the Beatles' time,
Yeah.
when there was all phonograph needles. And so the idea was that maybe we can use these magnetic changes to understand stress changes. And there are other things that cause magnetic changes. And so part of the idea was to decipher the difference between the non-seismological and the seismological causes of magnetic field changes. And there are space physical things, the Earth is bombarded with electrons and protons from the sun, and those cause magnetic changes, the daily variations and long-term changes, and they're higher in some places than in others. So we use linear inverse theory to try to decouple those effects from the space and from earthquake stress building up. And that experiment that we did to try to do that decoupling, I think led to part of my feeling that earthquake predictability is not really on the table, because decoding the magnetic signals was very uncertain and also very small. And the magnetic signals come from close by things in the crust of the earth. And the earthquakes themselves are resulting from, 5 miles below the surface. So the observable magnetic signals are not very strongly related to the earthquake stresses or the causes of future earthquakes. So that was a good fun experiment, but that's the scientific method in action.
Right.
We had these observations, we had some explanations for them, and then we tried to put them to the test and make some new observations. And what happened was we had to put thumbs down on some of the theories.
Dave, another nomenclature question. Long-term earthquake clustering. First, what is earthquake clustering, and is there a short-term earthquake clustering?
Good questions, both. Yes, clustering is much observed. Clustering refers to the temporal probability that an earthquake will happen given that another one has happened. And one of the ideas that has been debated at the Seismo lab and lots of other places is that stress builds up, earthquake happens, releases the stress, takes a long time for the stress to recover so that you can have another earthquake like the San Francisco earthquake. Clustering is the opposite of that. Clustering is what's observed. Mm-hmm. Clustering is aftershocks. And sometimes a big earthquake may be followed by another big earthquake or a bigger earthquake. So we don't know the limit of the size of earthquakes. So you may have a magnitude 8 earthquake in San Francisco. It doesn't tell you that there isn't a magnitude 8.5 in waiting someplace. The stress is already there, and the San Francisco magnitude 8 hasn't relieved all the stress. And the stress doesn't occur just in one place or in one large region. The stress is redistributed. There's some places near a fault where the stress becomes much higher. And that's what aftershocks are caused by, we think. We've got pretty good. Aftershocks are observed in almost all California type earthquakes, and only in very, very deep earthquakes, hundreds of kilometers below the surface, do we not really get aftershocks. And so aftershocks is a form of clustering, but the fact that big earthquakes might follow each other is also part of clustering. It's not observed by this San Francisco theory that the Earth has to rest. Mm-hmm, mm-hmm. And that's another reason why I'm not expecting earthquake prediction to come around.
Right.
Because these observations that, the Earth doesn't have to wait. It's ready to go just about any time.
David, in 1991, along with Jan Kagan, you wrote a retrospective look at the seismic gap hypothesis. What is that hypothesis, and how did it age over that decade?
That hypothesis is this one that there needs to be a time of recovery for earthquakes to happen. And the hypothesis actually resulted largely from earthquakes around the Pacific Rim involved in plate tectonics. And the hypothesis was confirmed by some cases where a big earthquake had happened and then a long time occurred, a long time between earthquakes, and then another big earthquake came. And so that seemed to give credence to the San Francisco type situation, but now in a lot of places around the Pacific Rim. And so some people did some studies of the time between these major earthquakes. And when an earthquake had not occurred for a long time in one place, that was called a seismic gap, and that's the recovering place. And so the seismic gap is thought to be a place where another large earthquake is due. And in fact, there are such places. But if you then take a statistical approach and look at all the places around the Pacific Rim, some places have had big earthquakes, some places have not had big earthquakes, some soon, some late, some never. When you try and use the same theory, you say, okay, here's an earthquake that occurred only 10 years ago. You shouldn't have another large one at that place. And then along comes an earthquake 5 years later. It's just as big as the one you had before. And so that's contrary to the seismic gap.
Meaning that it requires a new hypothesis or requires abandoning the hypothesis?
Some of both. It certainly requires abandoning that hypothesis as it was formulated,
Hmm.
because that hypothesis was pretty specific. It set out target dates for future earthquakes with some probabilities, so there's some statistics involved. Um, but given that there were 120 some locations around the Pacific Rim where there was good data and you could use this hypothesis to at least estimate when an earthquake of a given size was due. That was a really intriguing hypothesis. And I bought into it at first, and Kagan did as well, and lots of other people. And um, Frank Press bought into it big time, published some papers about earthquake prediction that were based in part on that hypothesis. But when we did the statistics, we found out that the earthquakes that were happening were more likely to happen soon after a previous earthquake rather than later. And there were some that occurred later. And so, there were some regions of agreement, but you have to look at the whole picture, not just a few examples. And so we said, okay, we can explain those few examples just by random occurrences. It takes, of course, some time for stress to build up. And when you have clusters, you may have a cluster of big earthquakes, and then at random, a time interval where there aren't big earthquakes, and then it can happen again. We don't know the causes of these clusters of clusters. But nevertheless, the idea that an earthquake has just happened and it can't happen again, that is really
Yeah.
not not in agreement with earthquake data taken generally, and also a dangerous idea.
Hmm.
We said, okay, you had a big earthquake. Now, can you relax?
Yeah.
Can you rebuild your cities after a San Francisco earthquake and not worry about future earthquakes for another 100 years?
Right.
Don't do that.
It's like you mentioned with COVID, we want it to be over, but nature may or may not have other plans.
That's right. That's right.
Dave, you mentioned geodesy earlier. Is there a portion in your career where you remember that becoming particularly relevant?
Yes. That has to do with this crustal deformation. So geodesy is a way of measuring positions of points on the Earth, and those respond to stresses. And so, to the extent that we can measure that response and then model that with a picture of the stress, that should tell you, you hope, about earthquake readiness. We haven't been able to put together pictures like that very much, except that when we measure deformation in the crust using geodesy, we find that the places that are deforming are the places that have more frequent earthquakes. So we can tell something about stress accumulation, but we can't tell the details of particular times. We can say that the rate of earthquakes is happening, but we can't put a date on any particular earthquake. And we can find that places that have lots of aftershocks also tend to have more deformation. So it's definitely a part of understanding what's happening in the earth, in the earthquake process. So it's very important. And I was involved in actually planning some experiments and using global positioning system in the very early days back in the late 1980s and 1990s. So I did get involved in some heavy duty field work on that. But there was also an earlier debate about the effect of deformation coming from leveling data. And leveling data is much less precise than GPS data that now we use. It precise than the laser interferometry that we use. But there was this idea that the crust had been uplifting in the area around um, Palmdale. And the story about the Palmdale bulge, you
Hmm.
probably
Hmm.
read something about that. I can tell you read a lot of my papers. So
Yeah, I do my homework.
yeah. And so there was this uplift of about a foot that was reported to be um, a result of uh, stress increase in the crust and maybe due to an upcoming earthquake. And again, Frank Press and I differed a lot on the interpretation of that. And it was due to, I mean, the reports that led to this theory were due to leveling data, and leveling data was occurring for lots of other purposes, not especially focused on earthquakes, but just determining property lines and where there are subsidence effects taking place due to water withdrawal, things like that. So leveling takes place throughout virtually the whole United States, and particularly along the coastlines, because we're interested in, have been for a long time, even before plate tectonics and global warming was part of the story. But sea level changes due to river flow and a lot of other things. So it's useful to measure the uplift or apparent uplift of what we call benchmarks, survey markers along the coast. And when it seems that um, the crust might have been uplifted at the coast, it may be just the opposite, that what's happened is water has lowered its level. So sea level might have gone down, and the reverse of that sea level might go up, and it looks like the solid part of the crust has gone down. So that's um, a source of geological and especially geodetic uncertainty. How do you understand the playoff between ocean change and solid earth change at this boundary?
Dave, a short
And
article you wrote in 1996, The Case for Huge Earthquakes. I can't help but smile. It sounds like you're writing in defense of huge earthquakes.
yeah, I am. And it's in part related to this idea about seismic gaps, because one of the parts of the hypothesis about seismic gaps is that when the stress reaches a certain level, it has to have an earthquake, and the earthquake responds to that level. And the size of that earthquake would depend on how much stress has accumulated. And so that's part of estimating what the time of the earthquake ought to be. But when you look at the data and you find that earthquakes aren't obeying those times, it could be because there's something wrong with the data, or it could be that maybe the earth could build up stress for a longer time and have a bigger earthquake. And part of the pre-existing story was that when you've had a San Francisco earthquake, that's the upper magnitude limit. And so you look for an earthquake of that size. And when the deformation has been big enough that you ought to have such an earthquake, then you should be concerned about that. Well, you should always be concerned about that, but not because of this limit. It could very well be that the San Francisco earthquake was not any kind of an upper limit to the ones that we're looking for. And so when you put together all the pieces in this story around the whole circum-Pacific rim and global earthquakes that have been observed, and we know their times and their magnitudes, and now we're waiting for something to happen. If that something is not a known size, but something bigger than that, then our paper was interpreting that data not that we like to have big earthquakes, but that when big earthquake happens, they're a cog in this story, and you have to abandon that idea that the earthquakes are limited by something you've already seen.
Dave,
We
given
don't
what
like
you've
big earthquakes, but they happen,
right,
and you
right.
have to understand that they do.
Given what you've already said about earthquake prediction, your paper same in 1996, hypothesis testing and earthquake prediction. Does that mean that hypothesis testing is a way to demonstrate the futility of earthquake prediction?
Hypothesis and going to testing hypotheses is a fundamental part of science. It's that scientific method we were talking about, and you get to the end, you got ideas, you make some hypotheses, and when your new data don't fit what you learned from the old data, you got to change your story. And it may be that you change your definition of what you're looking at, size of earthquakes, maybe, or it may be that there's something wrong in the story and you have to modify it. So the stories about earthquake prediction all involve some hypotheses, but to make it prediction in the sense that people want to deal with, you have to make the hypotheses not just general hypotheses, but specific ones. And say, okay, let's assume that earthquakes are going to be periodic. We have to tell you what the period is before it makes any sense. So you had an earthquake 1906, and is it a 100-year earthquake? Then it ought to be 2006, and we're overdue, and you better prepare more than you would otherwise because of that date. So that's where the testing comes in. You can apply that theory for San Francisco, but apply it to a lot of other places. Does it agree in those other places? And if it does, if you can, document it in a lot of other places, then it really is something you need to be especially prepared about. And that makes it a prediction. If it just occurs at random, some places it does seem to, agree with your theory about the time between earthquakes, and some other places it doesn't, then it's not really a prediction. It's okay, look out for earthquake. We already know that. But don't necessarily believe that a recent earthquake is protective and an old earthquake is more dangerous than others. So that's where the hypothesis begins to fall apart.
Dave, a more general public policy and science communication type of question. So for when scientists like you or Bob Geller tell the world, unfortunately, earthquakes cannot be predicted, that's not what the public wants to hear, right? They want to hear that earthquakes can be predicted. What have you learned about communicating the scientific process, doing the best job you can? What have you learned to be effective in communicating how science works to the public?
That is definitely a tough one. And you probably know that Geller and I and Kagan and Mulaja, this Italian co-author of ours, we all caught hell because of the publication, and including from Frank Press. Frank Press was really mad at me.
Really?
For that publication. And a large part of it was that we started out at the beginning to define what earthquake prediction was. And it wasn't saying that there's information about earthquakes that you can use for preparation. It's that if you expect a warning before an earthquake happens so that you can do something different from what you would do ordinarily, that's dangerous. That you should do that ordinary stuff knowing that earthquakes are going to happen sometime, rather than waiting for a telephone call that says, okay, earthquake on the way, get out of town. That was our message. People didn't read that definition of earthquake prediction.
Right.
They read the title. And we had a lot of discussion, particularly myself and Bob Geller, about that title. And, were we trying to say earthquakes could never be predicted under any guise, that we can never predict the location of earthquakes? We weren't saying that. And Geller insisted that we needed a punchy title. It got too punchy.
Mission accomplished.
We got punched.
So what exactly was Frank Press's concern? That you seem to have foreclosed on the possibility of future advances?
Yes. He was concerned, first of all, because he'd written papers that said earthquakes could be predicted. he was being contradicted. He didn't like that. But I think a number of people, including some people at the National Science Foundation who were funding our research, who said, you're going to cause a reduction in funding of earthquake science because of this paper. Well, that's a testable hypothesis. We have looked at the funding. The funding has grown.
Yeah.
Not as much as it should have, but as much as it had been in the past. So our paper had, no discernible effect on earthquake funding. And in fact, for the most part, it was ignored after, the punches that we got for having published that. And so the people who suffered were the authors, not so much as the readers of that paper.
Dave, just so I understand the nuances, so what about earthquake forecast models? When you were looking at short-term and time-independent earthquake forecast models, what does a forecast model mean in a scenario where earthquakes can't be predicted? What's being forecast?
The forecast we defined, it took a long time for the seismological community to sort of adopt a different terminology. But part of it was because of the reaction to that paper that we wrote.
Uh-huh.
They can't be predicted. So we wanted to say you can use information, and that information can be useful, but it isn't going to be the exact time and the exact place. So we said, now suppose you take a time interval of 10 years or 30 years is kind of the canonical time window now for a lot of earthquake studies. And you say, here are some places that within that 30 years, you would expect earthquakes over magnitude 7. That's a forecast. That's not a prediction. It's not saying the time, and it isn't saying that it must occur at that place. We're saying it's much more likely. So look at a lot of places like that, and they all have a probability of 50% over 30 years. Well, now you can do a test over all these places. How many of these places have had their magnitude 7s? And if it's more than 50%, you'd say, this is what we told you. And this is how you can prepare using seismological data without having to wait for a phone call to say run and hide when an earthquake is coming. So that's what we were aiming at. And now the community has adopted this forecast notion. And I think that's really a constructive improvement.
So even more nuances in the terminology. What about earthquake likelihood model testing? Is that not a forecast?
That is forecast.
That is forecast.
That is forecast.
Why not just call it forecast then?
That wasn't my choice, but that title comes, largely from the U.S. Geological Survey and putting together regional forecasts over all of California and Utah and things like that. And so they build a model of individual faults, and they say those individual faults have likelihoods, and then you add up all those faults and you get a regional probability of an earthquake occurring. So it's a good idea, but in science, there are lots of times when you use different words to describe the same kind of thing, And so I think it's been a very constructive enterprise to do these likelihood models. And then my job as a statistician is to try to then formulate some tests in which you can say this model is working or it's not working, and try to find if there's some reason that you need to modify the model and change it. And that's a work in progress.
And so the work on next day earthquake forecast, next day, does that get us closer to earthquake early warning, or is early warning only minutes or seconds?
Uh, so far, I think the real experimental work is on immediate occurrence. So the early warning means earthquake's already happened and it's been measured someplace else, and the seismic waves are on their way to you. And so the warning is to say those seismic waves are coming, not that the earthquake's about to happen. It's already happened. And there's a middle ground to that because of clustering. And clustering can mean earthquake happens and some aftershocks are also happening. And some of those aftershocks could be bigger than the first one that you knew about. So there's an enhanced probability of an earthquake happening at the place very near to where the first observed one is. So you can send out a warning on a magnitude 6.5 earthquake. And that warning is useful in the event that a magnitude 7 happens at that same place within minutes. So people get the warning, they duck and cover, they move to a place that's isolated from strong shaking, and then as long as they're patient enough to allow time for some aftershocks, then they're much safer than they would have been. And so that's a predictive kind of operation, but it's not predicting the earthquake, it's predicting the waves that have already started and they're on your way.
Dave, your contributions to the big survey in 2009, California earthquakes, 1800 to 2007. We established right at the beginning of our conversation that you don't see any cycles in earthquake history, right? So what then about the survey is valuable beyond that criticism of stamp collecting, right? That we're just collecting this data. What's the purpose of a big survey if you know already that there aren't cycles to be deduced from it?
I think the point there is science. People have used a hypothesis that's already been invalidated in many respects, but they're using this hypothesis to try and modify it just slightly to say, okay, the earthquakes themselves are not periodic, but some bunches of earthquakes are periodic. You can't really measure that interval because now instead of having earthquakes over tens of years, you might have it over hundreds of years or many decades. You can't observe many of those occurrences, many of those clusters, to put a probability on their occurrence at a certain rate. You just can't get data that goes back that far. So I think the hypothesis itself is very questionable, but it's worth posing it in such a way that you can begin to test it.
So
you can say it's untestable.
What are the takeaways then, absent the cyclic predictions, of engaging in such a big survey like that? What do you learn from that exercise?
I think you have to remind people that surprises are coming. And you can't rely on the particular time forecast, but you better rely on the fact that earthquakes are happening. You better not trust too much in the details, but absorb the basic message that earthquakes can be dangerous and you need to prepare for them. You need to take appropriate measures and you need to decide what those appropriate measures are. And so just mentioning the name earthquakes is constructive. Mm-hmm. And what I tell people who find out I'm a seismologist and they say, oh, when's the next one coming? I say, we don't know, but we know something, earthquakes are going to happen sometime. And you need to do some, obvious, simple preparations in your home. You need to have water in case the water main goes, and you need to have a place to poop when your toilet's back up. And you need to know where your children are if there's an earthquake at school. So things like that. Appropriate measures used a lot, but some people forget. So I say, when you hear a radio report or you see in the LA Times or the New York Times or whatever, an article about an earthquake coming, just take the word earthquake and say, oh, okay, I forgot to do the normal preparation. So make one step in improving your safety. It doesn't have to be everything you ought to be able to do, but make one step. At least talk to your kids' teachers and say, okay, what's likely going to happen if there's an earthquake on campus? How am I going to find my kid? How long should I be expected to wait? And so do those kinds of things. And at least that's something that's doable. People don't need to say, oh my God, earthquakes, stop the press. But I think that's constructive. And so when you have a survey about earthquake occurrence and maybe, oh my God, the big one is coming. Well, maybe the big one isn't coming, or the big one, it's not what to talk about. But just hear the word earthquake and say, oh, yeah, let's do something constructive.
A little bit of vigilance just to remind ourselves that earthquakes are on the way, even though we can't tell when and where.
That's right.
The RIP in your paper with Kagan and Geller, Characteristic Earthquake Model, 1884 to 2011, is that a rest in peace RIP?
Yes.
What were you making into an obituary about the Characteristic Earthquake Model?
That the model itself hadn't satisfied the data.
Uh-huh.
That it was, inconsistent with earthquake data. And the model itself had said that this 2011 earthquake in Tohoku, or offshore Tohoku, wasn't supposed to have happened. And this is a question of defense of big earthquakes. Okay, there's a big earthquake that you needed to recognize might be possible rather than impossible. So the RIP was saying, okay, that really defuses this hypothesis. Let's get rid of it and move on to something that is consistent with the data, at least.
Dave, in the last decade, your increased interest in looking at earthquakes at the global scale, global earthquake activity rates, were there advances in technology that allowed you to have literally a more global perspective of seismology?
I mean, there have been, all along. And at the time when this seismic gap hypothesis was formulated, which goes back to about 1980, in which some details had been presented, and that was specific enough that it could be tested. And so, we said it rejects the data reject that hypothesis. In the meanwhile, one could adapt that hypothesis by saying, okay, for one thing, some earthquakes have happened that, we couldn't have known about back in 1980, but now they've happened. And so if we believe this hypothesis, we have to change the dates because of these earthquakes. And then we can now measure much more precisely what happens in an earthquake. And so what used to look like a seismic gap because there hadn't been displacements due to previous earthquakes within this region that's now called a gap. When you look in more detail, you may find that there's some geodetic data that say some displacements have happened, but they weren't earthquakes. And so that would reduce the size of this gap. And there is a question about whether some parts of the earth may have displacements not caused by earthquakes, but just caused by smooth sliding along the surface of a fault. And that's part of the geodetical story. You can measure displacements at the surface of the earth. You've not had big earthquakes there, so that's telling you that there's some ability to relieve the stress without it being a giant earthquake. So all those developments lead to a much more precise picture of what is happening. And each earthquake can now be measured much more accurately than it could back in 1980. So all those are big improvements. Still, people tend to like this periodic earthquake seismic gap idea. You can't you can't stand it out.
Dave, what have been some of your more recent interest in paleo earthquakes and events?
Um, that grew out of some SCEC work in which Clarence Allen, who part of the Caltech story, and Carrie C., who was one of Clarence Allen's students at Caltech, and was about my vintage at Caltech. But a lot of other people have been involved in looking at faults, digging trenches across them, and finding out some sediments that had been displaced, presumably by earthquakes. And these sediments break through some layers, and some layers that are below a certain level have been displaced, and some ones above that level have not been displaced. And that's apparently because the earthquake was before those later layers were put on top. And so paleoseismology involves finding a time interval of the displacement of those sediments, because the earthquake had to be after the lower sediments, but not after the ones above. And so you can get a time interval between these displacements. And if those are earthquakes, it gives you a time interval between the earthquakes. And so there was a big study putting together a lot of paleoseismic data into a table in one of the SCEC reports. And in that table, for each of the sites, there were 30 some trenches that had been dug to get these dates. There is a date of the most recent displacement on each one of those sites. And I just looked at the dates and said, on average, they're about 20 to 25 years apart for the whole state. But when you add them all up, recently, there have been no displacements in the last century. What's going on? Mm. So I just did, some simple statistics on these dates and said, okay, could this occur at random? And, there are random variations at each site, and maybe somehow just by coincidence, they all have a delay from the last earthquake until now. But the chance of that happening at random is, less than 1%. And we usually kind of think of a 5% anomaly as being one we can tolerate, but 1%, no. So I wrote this up and said that there's a discrepancy here. And it's quite possible that the data themselves are not relating to earthquakes, but some other cause of the displacement. And that's still one that people aren't accepting. And you know, based on my history in dealing with earthquake prediction, I'm not surprised that people don't like that idea. But my first sort of study of this that I presented at the Seismological Society was in 2014. And so 8 more years have passed, and still no displacements at any of these sites. And I found that in Japan, or not in Japan, in New Zealand, there's a similar story. A bunch of sites on the faults, and none of them have had an earthquake type displacement in the last century. So I strongly believe there's something wrong with the data, but people know that I'm a contrarian. So that's where we are on that one.
Dave, just to bring our conversation right up to the present, what's the current state of play with the National Seismic Hazard Model?
That I don't know. Partly I've been unable to keep up with the developments over the last year. I don't know if I had a stroke in July of 2021. Yeah, and so that put me out of business for a while. And so I haven't been able to keep up with the meetings that go on to sort of plan the work that's going on. But I know that a lot of the plans are for similar kinds of studies that have happened in the past, and to sort of increase the importance in these studies of some purely theoretical modeling of faults, what they call physics-based earthquake forecasting. And I don't know exactly how they're going to do that, but I'm curious about what they're planning to do.
Dave, now that we've worked right up to the present, for the last part of our talk, I'd like to ask a few retrospective questions, and then we'll end looking to the future. So, over the course of your career, what do you see as your most significant contributions to the field?
I think it's an appreciation of the need for testing hypotheses, that we need to turn the hypotheses into detailed enough stories that a time interval like 10 years or so can help to validate or invalidate the hypotheses that we're dealing. So more focusing on the scientific method, putting the whole picture together, rather than individually trying to work on just an observation or just a hypothesis, but taking observations, hypothesis, and logic and using those things. So that's, I think, the most important. That's where I see the scientific community doing great work, but not putting things together in the way that Kei Aki recommended when he formulated the Southern California Earthquake Center.
To go all the way back to when you were an undergrad at the Seismo lab and you were, taking in all of the debates of the day, from then to now, what debates have been settled and what remain as open as when you first encountered them?
I think none of them have been completely settled.
That's good. That's good.
The debates all have some foundation in correct observations. And the difficulty is generalizing those to look at some places where the specific forecast or specific hypothesis is made, and it may be made retrospectively. You say, oh, I see what happens, and maybe you look in some one other place and they say, yeah, it happened again. So that gives some support to the theory. But what needs to be done is to look at a number of different places and get a more representative set of data for that. And it's hard to do because sometimes you get funding for doing a certain experiment and not for another one. Um, so I don't see any of the things that have been debated really being resolved. But there's one case, which is this Palmdale bulge that goes back to the late 70s and early 80s. Um, that was due to some stress accumulation that may result in earthquake on the San Andreas. Um, Nobody except a handful of us have come by and said the data are not correct, which is the case. That the leveling data that were used in that forecast, that observation of the uplift itself didn't happen. And there is a fellow at the USGS named Ross Stein. I don't know if you've encountered his name, but he had been part of the original leveling studies and so forth. He went back and looked at data, and he agreed with us that uplift didn't happen. And people resisted, that contradiction for some time. But about 10 years later, there was a review of U.S. Geological Survey studies in California, and they did not mention the Palmdale Bulge. So I regard that as a settlement of that debate, even though it wasn't a definitive kind of admission that there was a problem. I just said, what problem?
Dave, the fact that you say that really none of the science is settled is a perfect segue to my last question, looking to the future. To the extent that you have opportunity to interface with students who might be curious about where the field is headed, where they might focus their energy, the fact that so much of the science is still open and, ready for additional investigation, what do you see as the most interesting and fruitful areas of focus in the coming decades in seismology and geophysics?
That's a wide open question. Clearly, better observations are always a part of the focus. And you probably heard about some of these studies that involve optical glass fibers being stretched, and you can measure the length of that stretching from one point to a tiny, tiny little crack in the optical fiber that tells you displacement has taken place. And these optical fibers are everywhere. And so that's a really big advance, I think, in seismological and geological observations. So using these data and getting much more specific locations of earthquakes and descriptions of earthquakes can be helpful in testing some hypotheses. And then there are a lot of hypotheses about how you can derive geodetic information from new kinds of observations and then put those together with the story of stress buildup and deformation and possible interaction with earthquakes and the result of earthquakes. And when earthquakes happen, we need to know not just that there was shaking, but what it's done to the surface of the earth and to the subsurface part of the earth down to 5 miles deep and deeper. And when we can measure those things, we can get some hypotheses about stress transfer and what is the effect of stress, what causes it, and then what can result in it. So I think those things are really exciting openings for new science and new ideas. And then testing. I think, it's interesting to get people who are not seismologists involved in testing hypotheses. Okay, how do you take some of these hypotheses and take some data that might be relevant and put them together? And now say, how long does it take before you would know if a hypothesis is correct? And some of these same people who are working on COVID are also now interested in those kind of tests. What are the results of things that we can observe? So I think there's plenty for young people to do, and we could talk a lot about that. And of course, there are proposals being written to involve young people in those kinds of questions.
Dave, this has been a terrific conversation. I'm so glad we were able to do this. I'd like to thank you so much.
Well, you're very welcome.